for what we have for this differential equation, if I look at trying to solve by using Laplace transforms, okay, and so we have with the first term, we have the second order derivative of x with respect to t, and if I take directly the Laplace transform of this, so I have s squared times the Laplace x sub s minus s times x naught minus x prime naught, and x naught is at 2, x prime naught is at negative 3, and so we have s squared times the Laplace x of s minus 2s, and minus negative 3 translates to the addition of 3. And for 8 times the Laplace of the first order derivative, okay, so I have 8 times the quantity of s times the Laplace x sub s minus x naught, but we have x naught at 2, and we have with the distribution, so we have 8s times the Laplace x sub s minus 16, and for the correspondence to 15x, so if I take the Laplace of 15x, or 15 times the Laplace of x of t, this will be 15 times the Laplace x sub s. And for the coefficient 0, okay, now if I had a non-negligible constant, the Laplace transform would be that constant divided by s. However, for 0, 0 over s goes to 0. And setting things up in terms of the Laplace transform terms, okay, so looking at partitioning, okay, this is what I have in the setup. And I'm going to be looking at combining like terms together. So we have for the Laplace variable x sub s, so you have s squared plus 8s plus 15, and I can just put together, so you have s squared plus 8s plus 15 quantity times the Laplace x of s. And what I can do is I can just move the other terms, okay, on the other side, those that are not attached to the Laplace x. And so we have, so we got negative 2s, and if I shift over, so we have 2s, and we got 3 plus negative 16 is minus 13, and if I move to the other side, so that's going to be 2s plus 13, and isolating the Laplace x sub s. So we have 2s plus 13 all over s squared plus 8s plus 15. And here we have a trinomial that is factorable. So we're going to have in the denominator, then we have the quantity of s plus 5 and that of s plus 3. And I can set things up in terms of partial fraction decomposition. And I'm going to go ahead and get to that. Okay, so for the partial fraction decomposition, we're going to have in the setup, and if we use the zeros of what we have for s plus 3 and s plus 5, if I set s equal to negative 5, a comes out to negative 3 halves. And we have on the other hand, if I set s to negative 3, a cancels out, and we have b equal to 7 halves. Okay, and so this will be the partial fraction decomposition. So this is what I'm going to have for the Laplace x of s. Now in terms of solving for x of t, okay, I'll be taking the inverse Laplace transform of what I have with the terms from the partial fraction decomposition. So I'll be looking at negative 3 halves of the inverse Laplace of the reciprocal of s plus 5, and I have plus 7 halves of the inverse Laplace of the reciprocal of s plus 3, and for the reciprocal of first order binomials in s, okay, we're going to have at the root, again, we have e to the at, okay, and in this particular case for the first term, okay, now s plus 5 is s minus negative 5, so the a value is going to be negative 5. So I'm going to have negative 3 halves of e to the negative 5t. And for the second term, okay, we have s plus 3, which is s minus negative 3. And we have for the inverse Laplace transform of the reciprocal of s plus 3, that's going to be e to the negative 3t. And so we have for the final result in this one, we're going to have the solution x of t is equal to negative 3 halves of e to the negative 5t plus 7 halves of e to the negative 3t. For the next item, we have another second order differential equation, and we have the second order derivative of x with respect to t plus 3 times the first order derivative of x with respect to t plus 2 times x with respect to t is equal to t. And for the initial conditions, we have x naught is equal to 0 and x prime naught is equal to 2. And if I take the Laplace transform of each of the terms, okay, so for the second order derivative, I have s squared times the Laplace x sub s minus 2. And again, so x naught is 0, x prime naught is equal to 2. Okay, and we have for 3 times the Laplace of x prime of t. Again, so we have 3 times the quantity of s times the Laplace x sub s minus x naught. Again, x naught is 0, so this goes to 3 times s times the Laplace x sub s. And for 2 times the Laplace transform of x of t, that is equal to 2 times the Laplace x sub s. And for the Laplace transform of t, again, that is equal to 1 over s squared. And as I applied the Laplace transform translations to what I have upon setting up the equation in terms of Laplace transform terms. Okay, so this is what I have. And looking at combining what we have on the left-hand side with the Laplace x sub s attached. Okay, so we have s squared and 3s along with 2. And I have times x sub s. And if I move the 2 to the other side, so we have 2 plus 1 over s squared. And if I combine 2 and 1 over s squared, so in this case, this will be 2s squared plus 1 all over s squared, and isolating the Laplace x sub s. So I have 2s squared plus 1. We have all over s squared. And we have times the quantity of s squared plus 3s plus 2. And you can either factor out the trinomial beforehand before even dividing. But in the case of what we have in the layout, so again we have s squared. And for s squared plus 3s plus 2, this will factor out to the quantity of s plus 2 times that of s plus 1. And okay, so we're looking at performing partial fraction decomposition. So looking into the partial fraction decomposition, the first factor, s squared, you can either treat as a quadratic factor, where you can set this up as as plus b all over s squared, or you could treat it as a repeating linear factor, where you can split up this expression, where you have a over s plus b over s squared, and you just keep adding fractions until you get to the degree of the original monomial factor. Okay, and then we have c over s plus 2 plus d over s plus 1, and if we multiply everything out by s squared, s plus 2 and s plus 1, we got this particular setup. And so utilizing the zeros of s plus 2 and s plus 1, if I set s to 0, I get to b is equal to 1/2. And for s equal to -1, our terms in a and b and c go out, and we are left with d equal to 3, and if I set s to -2, okay, those expressions containing s plus 2 will go completely out, and the one that remains we have in the variable c, and we have in calculating, and we have that c is equal to -9/4. Okay, so again, left hand side you got s at 0, so you have 1, and 2 times the square of -1 plus 1 is 3, -2 squared is 4 times 2 is 8 plus 1 is 9. So this is where I get these values. Now, I've used up the zeros, and I have to solve for a, and I just picked an arbitrary value, and my recommendation is whatever you choose, you want to keep the absolute value as low as possible. Okay, and I just chose the number 1. Okay, and so we have for 2 times the square of 1 plus 1, that is 3, and you got 1 times 3 times 2, a, so you have 6a, and b, I have 1/2 times 3 times 2. From c, I have -9/4, and 1 squared is 1, 1 plus 1 is 2, and d, we have already established at 3, 1 squared is 1, 1 plus 2 is 3, and looking at taking the products and combining the constants, we have 6a is equal to 9/2, and we have with division by 6, a is 9/12, which is reducible to 3/4. And so we're going to have, for the partial fraction decomposition, we're going to have this set of items. And this is what we're going to have the Laplace x sub s to be set equal to. And so we have x sub s equal to this set of terms. And for what we have in solving for the function x of t, so we will just be taking the inverse Laplace transform of what we have in s. Okay, so inverse Laplace transform of 1 over s. Okay, so this part will go to 1. Then we have plus 1/2 of the inverse Laplace transform of the reciprocal of s squared. Okay, well that is going to go to t. And for -9/4 of the inverse Laplace transform of the reciprocal of s plus 2. Okay, and in this one, okay, so we're going to have e to the -2t. Then we have plus 3 times the inverse Laplace of the reciprocal of s plus 1. And that one we will have at e raised to the -t. Okay, so we have for the end results here, we'll have x of t is equal to 3/4 plus t over 2, or 1/2 of t. We have -9/4 of e to the -2t, and we have plus 3 times e raised to the -t, and that will be the final result in this equation.